Hello everybody and welcome to Nuclear Physics Lesson 4. In the last lesson we looked at the inverse square law for gamma decay and we came up with a general equation that I was proportional to 1 over r squared, where I is the intensity of the gamma radiation that we are detecting at a certain point and r is the distance between the detector and the source. We also had a chat about background radiation and some of the safe handling rules for when we're handling radioactive sources. What we're going to move on to today then is to have a look now at the mathematics behind how nuclear decay works. Firstly then, when we're studying radioactive decay, we need to understand that radioactive decay is a completely random process. Now, in order to model that, in order to demonstrate that, what we're going to think of is just using a normal six-sided dice. So there's a bit of a thought experiment there on the screen. What we're going to do is we're going to imagine taking 100 six-sided dice and we're going to roll them. If a dice rolls a 1, then we're going to imagine that that is a radioactive nucleus that has decayed. Therefore, we can see that the probability of any given dice out of that set of 100 decaying is going to be exactly 1/6. So we know that the probability of decay is 1/6. When we roll these 100 dice then, on average we're going to expect that 1/6 out of that 100 will roll a 1. Now sometimes it may be more than a sixth, sometimes it may be fewer than a sixth. But whatever happens, we know that if we did this experiment lots and lots and lots of times, it would probably end up averaging out that a sixth of them would end up rolling a 1 as we make that sample bigger and bigger and bigger. Now obviously 100 divided by 6 isn't necessarily a nice number. 100 divided by 6 is actually 16 and 2/3, and obviously we can't have 2/3 of a dice decaying. But as I said, as we increase the numbers, we are going to get closer to a sixth decaying when we roll 100 of them. So what we can do in our thought experiment is we can start to sketch ourselves a table. Okay, and we can say number of rolls and we can say dice left. Now after 0 rolls we know that we started with 100 dice because that's exactly what it says in our little thought experiment. After 1 roll we're expecting roughly a sixth of those to decay. So let's just say, for sake of argument, that the number decaying is exactly 16, and we'll forget that 2/3. What we're therefore left with is 84 dice are remaining. For the next part of our thought experiment, we're going to take those 84 dice and we're going to roll them again. So we're going to take 2 rolls now. Now fortunately I know that 84 divided by 6 is 14, which hopefully you can see why I chose to have 16 dice decay in the first instance, just to make the numbers nice for us. So let's say that we do get exactly 14 decaying and we will therefore be left with 70 dice. Let's do the same again. Let's roll those 70 dice that are left. 70 over 6 here is actually 11 and 2/3. So let's just say we're going to round that up to 12, and 12 of those 70 dice end up rolling a 1. What we will be left with there is 58. Let's do a 4th roll. 58 divided by 6 is 9 and 2/3. So let's say that we've had 10 decay, round it up again, and we've therefore got 48 dice left. Let's do 1 more roll, so we're going to have a 5th roll. Now a sixth of 48 is exactly 8, so let's take that down to 40 dice remaining. Now, admittedly, those numbers that I've chosen there are slightly idealised. I chose them at different places to actually make our maths work out a little bit better. But hopefully you've got enough of an understanding of probability from maths lessons to know that if we repeated this experiment over and over and over again with 100 dice and kept on rolling them, eventually we would average out to something very similar to the numbers that we've got there with a sixth decaying every time. Alternatively, if we took more dice, not just 100, we could take 1,000. You could even use a computer to program it so that we could imagine 1,000,000 dice all being rolled at once. Then the way that probability works is, on average, we are going to end up with a sixth of them decaying every time we roll them. What we end up with then is, if we try and sketch a graph, and obviously on the next screen I'll show you a better version of this. On the y-axis we're going to have dice left, how many dice are remaining, and on the x-axis we're going to have the number of rolls. Now we know that we started off with 100 dice remaining, and I'll just put 50 there because that's halfway. I'll just mark some numbers on. 75, 25. This is obviously only a sketch graph. As I said, we'll have a look at a proper graph in a moment. So we know that after 0 rolls, in other words at the start, we had 100 dice remaining. So we've got a data point there. Let's just put some numbers on this x-axis. We'll just do the first 4. After our first roll we had 84 remaining, so we've probably got a data point roughly there. After 2 rolls we had 70 remaining. After 3 rolls we had 58, and after 4 rolls we had 48. And what we can see there is not brilliant on the screen, but a bit of a curve. So here now is a better version, a neater version of the graph that I was just sketching on the last slide. And what you can see is this nice curve coming down, very similar to what we've just drawn. Now the shape of this particular graph is known as an exponential decay curve. In the next lesson we will look properly at the mathematics behind the exponential decay curve, and we will eventually be able to get an equation that completely describes the shape of the graph that you can see on the screen. But for now I just want to point out a couple of features of this exponential decay curve. Now if we imagine, let's get away from the idea of dice now and let's get on to what we're really trying to study here, and that's the number of radioactive nuclei that are remaining. So on the y-axis we will put nuclei remaining. Now at our initial point before we actually start any decay, I'm going to call this n0. So n for number of nuclei, and noughts, that's the number at time is equal to 0. So it's the number of nuclei that are remaining before we actually start timing and studying this decay. Now one of the good features of an exponential decay, if we come from n0 up here and we come now to n0 over 2. In other words, we've halved the number of nuclei. If we trace across to the graph and then we trace down, we can see that it's taken 2 time periods on this graph in order to halve the number of nuclei that we've got. If we take that half and half it again, we end up with a quarter of the initial value. Now if we trace across and trace down, we can see that another 2 time periods have elapsed. We can do it a third time, and I'll just change colours so it's becoming less confusing, and come down to an eighth of the initial number of nuclei, trace across and trace down, and we can see that again another 2 time periods have elapsed. The technical name for one of these time periods is known as the half-life. And half-life takes the symbol of a little t with a subscript of a half. So here now is the proper definition of half-life. So the half-life of a radioactive substance is the time taken for half of the nuclei of a large sample to decay. Now, one of the key phrases in here is large sample, and again we need to make sure, because of the discussions that we had earlier about probability, we know that the larger a sample, the better the idea of probability works, and the closer that probability will come to true values as we make those samples large. Now, the good news when we're talking about radioactive substances is a lot of the time we're dealing with extremely large numbers. For those of you that do chemistry, you'll know that Avogadro's number is 6.022 times 10 to the 23 per mole. So what that means is that if we have 1 mole of a substance, it contains approximately 6 times 10 to the 23 nuclei or atoms in 1 mole of that substance. Now, of course, if we're dealing with something like uranium-238, 1 mole will be 238, roughly 238 grams. So actually, if we were to take something like a kilogram of uranium, we would have 4 moles of uranium, or just over 4 moles of uranium, and we would have 10 to the 24 of the order of 10 to the 24 atoms of uranium in that 1 kilogram. Now, obviously, when we're getting up to that kind of order of magnitude, 10 to the 24, that is definitely a large sample, and therefore the probabilities are going to work well enough to mean that we can make a proper measurement of our half-life. So if we just bring back that graph from the last slide a moment, and obviously we have N0, we can see that the time taken for half of them to decay, so coming down to N0 over 2, is this time 2. So our half-life in this example would be 2 time periods. Now that could be 2 seconds, it could be 2 minutes, 2 hours, 2 days, 2 years, it could be 2 anything. We haven't put a unit on that yet. Let's just say, for sake of argument, that we are looking at 2 seconds. As we said before then, once we've got to that 2 seconds, we've got half of the initial sample remaining. After another 2 seconds, so after another half-life, we have N0 over 4. So we've taken the half that we originally had and we've halved it again. What we can say then is that in general, after so many half-lives, so let's just say after n times the half-life, the number of nuclei remaining, okay, so n, the number of nuclei remaining, will be N0 divided by 2 to the power of little n. So I know we're using a lot of n's here, but this n here and this little n here are the same. What we can see then is that if the half-life is 2 seconds, as we've said here, then after 4 seconds, well, 4 seconds is 2 times the half-life, and we've gone from N0 to N0 over 2 to the power of 2, well, that's just N0 over 4. If we go another half-life, so we go to 6 seconds, and 6 seconds here is 3 half-lives, then we've gone from N0 to N0 over 2 to the power of 3, that's n0 over 8, and we can see that this value here, if you look at the scale, is n0 over 8. Now, so far what I've done is I've only used integer values for half-life, but actually this number here, this n here, can be any value. It doesn't even have to be an integer. We can have that as any number. So just to show you that before we move on and this graph becomes too messy, well, let's say what happens after 3 seconds. Well, 3 seconds is 1.5 half-lives. So we can calculate the number remaining. It will be n0 over 2 to the power of 1.5. And what that tells us is at least the decimal that's left will be about 0.35 times the initial value. So if we come up from 3 half-lives and across, this should be around about 0.35. Because the scale works in eighths, this line here will actually be 0.375, and therefore we can see 0.35 is just below that value. Now, of course, that half-life that we looked at will differ from nucleus to nucleus and from different isotope to different isotope. In order to demonstrate that, we've got a few sort of different dice on the screen. For those that aren't necessarily familiar with different shapes of dice, the orange one we've got here has 4 sides, the yellow one has 8 sides, the green one has 10 sides, the blue one has 12, and this red one has 20 sides. Now, if we played that same game as earlier again, and we roll them, and if we get a 1, we're saying that that dice is going to decay. With the 4-sided dice that we've got here, we can see that a 1 will come up far more often than it would on a 6-sided dice. Therefore, we would be expecting roughly a quarter to decay each time. So we might start with 100 after 0 rolls. After 1 roll, we'd expect 75 to be left. After 2 rolls, well, a quarter of 75 is somewhere between 18 and 19. So let's say 19, which takes us down to 56. After 3 rolls, a quarter of 56 is 14. So that's going to take us down to 42. So you can see that for a 4-sided dice, that's going to decay a lot quicker. If we were to take a 20-sided dice, at least colour code it a little bit here, then we would only expect roughly 1/8 of every 20 to decay when we roll them. So we would start with 100, but after 1 roll, well, a 20th of that is 5, so we might have therefore 95 remaining. After the second roll, you might only get 4 decay, and after the third roll it might be again 3 or 4. So we can see that we've completely changed the probabilities between the dice. We're still having the same idea that we're trying to roll a 1, and it's only if we roll a 1 that they decay. But as we change the probabilities by changing the numbers on the dice, and we can obviously think about this from a nucleus point of view, that we're changing the probability that particular nucleus is going to decay at a given time, more or fewer will end up decaying every time we have 1 time period, or if we look at it from the dice point of view, 1 roll of the dice that are remaining. It's important then at this point to understand this idea of random nature, and if you have a look at the definition on the screen, it's impossible to predict exactly when an individual radioactive nucleus will decay. If we take that from our dice point of view, if you kept on rolling a normal 6-sided dice, there is no way that you can predict on exactly which roll you're going to get it to roll a 1. You know that if you keep rolling it, eventually it will roll a 1. Okay, it may take a little bit of time. You might do it on the first roll. It might take you, if you're really unlucky, it might take you 100 rolls to actually get it to roll a 1. But you know that eventually it is going to roll a 1 if you keep doing it. Going back to the definition then, but it is possible to predict how many of a large radioactive sample will decay in a given time. So once again, we know with our dice analogy that if we rolled 6 million dice, we would expect roughly 1 million of those, a sixth of those, to have decayed. And the larger that sample, the better that estimate and the better that prediction will end up becoming. Here now is your question for this lesson. So a certain radioactive sample has a half-life of 8 days. What percentage of nuclei of the initial sample will have decayed after 30 days? As usual, pause the video at this point, have a go at it yourself, and we'll come back in a moment and have a look at the answer. So for this question, the first thing that we need to ascertain is exactly how many half-lives 30 days means. So if we do 30 divided by 8, we get 3.75 half-lives. Now the number that are left will be the initial number divided by 2 to the n, 2 to the little n, where little n is the number of half-lives. So that will be n0 divided by 2 to the power of 3.75. And our calculator tells us that that is 0.0743, etc. Now that is a decimal. If we're going to convert that into a percentage, we multiply by 100, so what we get there is 7.4 let's leave it, 7.43% will be remaining. But of course the question is asking us how many have decayed, so in order to work out how many have decayed, it's just 100% subtract that. So the number that have decayed, the percentage that will have decayed, will be 100 minus 7.43. And what that gives us, if we look at the full calculator answer, it says 92.567, etc. So therefore, if we round that to 3 significant figures, we have 92.6% of our radioactive nuclei have decayed after 30 days. So that's it for this lesson then. We have looked at the random nature of radioactive decay today and come up with the definition that it is impossible to predict exactly when an individual radioactive nucleus will decay, but it is possible to predict how many of a large radioactive sample will decay in a given time. And then we also came up with our definition for half-life, and the half-life of a radioactive substance is the time taken for half of the nuclei of a large sample to decay. So obviously that's it for this lesson then. Next lesson we're going to try to put an equation onto the exponential decay graph and to come up with obviously a more mathematical way and a better mathematical way with the equation of working out exactly what's going on in these large radioactive samples. As usual, if you've got any questions, please get in contact with one of us, and I'll see you next lesson.